Hey Math 1030, this video is for our first lesson in Unit 8. It's called Growth Linear versus Exponential. So we're going to first start focusing on thinking about linear things and exponential things and look at a couple of different examples of that. And then we're going to shift our focus into exponential. So imagine that you have two communities, Straight Town and Power Town. Each of them has a beginning population of 10,000. Straight Town is growing at a constant rate of 500 people per year. So you can see the graph of Straight Town there. It's just going up by 500 people each year. So just nice linear growth there. Power Town is growing at a constant rate of 5%. So one of them is growing by a set amount of people, one of them is growing by 5%. So the graph of Power Town would actually end up looking like this. Power Town's population is almost the same as Straight Town for the first, probably 5-7 years. Very similar. But then after that, Power Town just takes off growing. So those are the two basic types of growth patterns. The first one, linear, that occurs when a quantity is growing by the same absolute amount, like our 500 people in Straight Town. Exponential growth is when the growth occurs by the same relative amount, usually given as a percentage over each unit of time. So these two terms, linear and exponential, can also be applied to decreasing quantities. In that case, we would say linear decay is when it is going down by the same absolute amount. Exponential decay means that the quantity is decreasing by the same percent each unit of time. So we're going to look at 4 examples and decide if they are linear or exponential. And then we're going to do a calculation involving it. So first of all, the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population 4 years ago was 750, what is it today? So in this example, it looks like it's going up by the same absolute amount, which is 50 students. So that would be linear growth. So now calculating the population today, I like to think about what I'm starting with. We are starting with 750 students, and then we are adding 50 each year for 4 years. So 50 for the first year, 50 more the second year, 50 more the third year, 50 more the fourth year. Or another way of thinking about it would be plus 50 times by 4 for the 4 years. So either way that you think about it, you get a total of 950 students. Okay, the next one. The price of milk has been rising 3% per year. If the price of a gallon of milk was $4 a year ago, what is it now? So in this case, it's rising by 3%, and that's a percentage, which is a relative change. So this is an exponential growth. Okay, so to figure out the price now, there's several ways that you could do it. I just want to show you this way of thinking about it because I think it's pretty easy for doing the calculations you need to do. The price is going up by 3%. Well, it still costs 100% of what it cost before, but it's an additional 3% each year. So that would be 103% total. In decimal form, that is 1.03. This is what I'm going to use in my calculations. So I take the starting price, which was $4, and I just multiply it by that relative change with the 100% included as well. So times by 1.03. So that gives me 100% of the cost of the milk plus the additional 3%. So if we do that calculation, we get $4.12. And this is our answer because it just asked us after 1 year. But on your homework, I think most of them ask you for like 2 years or 3 years. So this would be after 1 year. So I just want to show you how to get additional years. So you would take that starting amount now, 412, and then also still just multiply it by 1.03 to get the next year, which is 424. And it's kind of looking like I'm just adding 12 cents, but I am not. This is a relative change. So to get the next year, if you were doing like, 3 years, for example, you would start with your current price, 424, and multiply that by 1.03 to get, so that was year 2. For year 3, we start to see that change, not 12 cents anymore, $4.37. So you would just multiply by that decimal form each time for however many years you need to. Okay, so let's look at another one. Tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment for $1,000 3 years ago, what is the depreciated value today? So first of all, let's decide if this was linear or exponential. Well, this is by a fixed amount, an absolute amount. So that would be linear. Percentages would be exponential. So now let's do our calculation. So the starting amount is $1,000 and it's decreasing by $200 per year. Let's see, I want to write year 1 up there. So minus 200 for the first year, minus 200 for the second year, minus 200 for the third year. Or you could think of it as $1,000 minus $200 times by 3 years. Either way you think about it, you get that the equipment is now worth $400. Okay, last one of these. The price of a high-definition TV set has been falling by about 25% per year. If the price is $1,000 today, what could you expect it to be in 2 years? So first of all, let's decide if it's linear or exponential. It's falling by 25% per year, so that's a relative change. So that is exponential. And now let's figure out how much that price will be in 2 years if the price is falling 25% per year. So before with the exponential, we did 100% plus 3%. Well, this is a decrease of 25%. So if we think about it the same way, except we're subtracting because it's a decrease, that means the price is only going to be 75% each year. So that's what we're going to use. We're going to use a decimal form of that, 0.75. So we take our starting amount. Starting amount is $1,000, and we're going to multiply it by the 0.75 for 75%. It's only 75% the next year. So 1,000 times by 0.75 for the first, after 1 year, the price is $750. And then we need the price after 2 years, so we'll take that $750 and multiply it by 0.75 again to get $562.50. And if it was 3 years, we would just repeat that process. So $562.50. Okay. So here's our graph from Powertown and Straighttown again. You can kind of see if you look at it that starting with the 10,000 people, the population doubled to 20,000 after about 14 years. And if you look at another 14 years, you can see that it doubled again. And then after another 14 years, it doubled again. So that repeated doubling is, or that amount of time it takes to double is called doubling time. And we will be working a lot with that in 8B. So we're going to look at some parables now that relate to doubling. They're kind of fun. So the first one has to do with a chessboard. So legend has it that when chess was invented in ancient times, the king was so enchanted that he said to the inventor, "Name your reward." And the inventor said to the king, "If you please, put 1 grain of wheat on the first square of my chessboard, then place 2 grains of wheat on the second, and then 4 grains on the third, and 8 grains on the fourth, and so on, so doubling each time." The king gladly agreed, thinking that the man was a fool for asking for a bunch of grain when he could have had gold or jewels. But the king never finished paying the inventor because that's a lot of grain, and instead had him beheaded. So let's look at this scenario for a minute and then we'll answer a couple questions related to it. So we're just doubling the amount of grain on each square. So doubling, doubling, doubling. I'm going to write out some powers of 2 really quick. So 2 to the 0 power is 1. 2 to the power of 1 is 2. 2 squared is 4. I just wrote 6. Oh my gosh.
Sonic 7's up.
Okay, 2 to the 4th, 16. And these numbers should look familiar because they're kind of the same numbers from our list over here on the grains of wheat. So the first square had 1 and the second square had 2. So it's not just 2 to the power of the square. It's 1 less than that. So for the nth square, our equation that we can use to calculate is a power 1 less than that. So 2 to the n minus 1. So in theory, like on the 15th square, for example, we would have 2 to the 14th grains of wheat. Now let's think for a minute about how many grains so far. So at first, we only have that first square, so there's only the 1. But then on the next square, we add 2, so now we have a total of 3. And then on our next square, we add 4. So we have a total of 3 plus 4 is 7. And then on the next square, we are adding 8 more for a new total of 15. And then we're adding 16 more for a new total of 31. Well, these numbers don't. Oh my gosh, look at my brain. I wrote a 36 there and I didn't even notice it. 32. Okay, so you might notice that these numbers that I wrote in blue, they don't match this list. But on the 5th day, I have 31, and 2 to the 5th is 32. So it's 1 less. And let's look at the 3rd day. On the 3rd day, we have 7 total. Well, that's just 1 less than 2 to the 3rd. So, our formula for the grains of wheat placed on all of the squares up to the nth square is 2 to the power of n subtract 1. So these two formulas look almost identical. They look very, 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 very similar. just the location of the -1 is the difference. So on square n, the -1 is in the power. If you're talking about the total amount of wheat so far, the -1 is not in the power. So let's answer a quick question. How, or two, I guess. How many grains of wheat should be placed on square number 50 on the board? Well, we're just talking about that one square, that 50th square. So we're going to do 2 to the power of 50 minus 1, which is 2 to the power 49. 2 to the power 49. And it's shocking how much wheat there is. 5.63 times 10 to the 14th. Now, I don't remember how many decimals MyMathLab wants you to put in here, so just be mindful. I wrote down 2 decimals right here on my answer box, but and it might ask you for 2 decimals. I don't remember, but it may ask you for more, so just put however many decimals it asks you for. So that was just on the square number 50. This next one is saying how many grains of wheat would be placed on the first 50 squares, and that's plural. That's all of them up to the 50th square. So for this one, we're going to calculate 2 to the 50th power and subtract 1. So make sure you go over to get out of that power when you're doing this one. So 1.13 times 10 to the 15th power. Okay, the last one is about the weight of the grain. So in the original question, it'll give you a little bit of information about converting. So it says each grain of wheat is 1/7,000th of a pound and a ton is 2,000 pounds. So those are, we're going to use those to get our last answer. What is the weight in tons of the wheat on the first 50 squares? Now, first of all, we don't want to use our rounded answer. We want to use all of the decimal places. So we need to use our full number. Now, luckily, with our calculator, that's really easy. You don't even really need to write this out. I'm just writing it out because I'm making a video. But we need to use all of the decimals that our calculator is giving us. So this is the number of grains of wheat. So to convert into pounds, we're going to divide that number by 7,000. And on some of the questions on the homework, it just asks you to give the answer in pounds, in which case you would just divide by 7,000 and be done and put your answer in. Now, on the calculator, I already had that 1.25899 blah, blah, blah in the screen. So I just hit divide by 7,000 and it's going to use that full decimal. So this is now in pounds. And then for this question, I want it in tons. So I'm going to also divide by 2,000 to convert to tons. And again, I can just type divide by 2,000. It will take that previous answer and divide it. It does want our answer in scientific notation. And sometimes if the answer is big enough, it'll just throw it into scientific notation for you. But if it doesn't, you can either convert it into scientific notation on your own. 3, 4, 5, 6, 7, if I counted right. Or if you prefer to let your calculator convert it, you can hit mode and then just go down to scientific notation, hit enter, then quit, and then grab that number and hit enter and it will convert it. So that would be how much weight the grain had in tons. Now, like I said, some of them ask for pounds, in which case if it asked for pounds only, you would stop right there and get your answer. If it asked for, wow, Sometimes the things I write answer in pounds. If it asks for tons, then do the divide by 2,000. Okay, super fun with the grain. And we have two more parables. I think the grain one is the hardest though. So one lucky day, you meet a leprechaun who promises to give you fantastic wealth. He hands you a penny and disappears. You head home and you do what any logical person would do. You put that penny under your pillow. The next morning, to your surprise, you find 2 pennies under your pillow. The following morning, you find 4 pennies. The morning after that, it's 8 pennies. And apparently, the leprechaun gave you a magic penny. And while you sleep, the magic pennies turn into 2 magic pennies. So, we start out with that 1 penny that he handed you. We're calling that day 0. So you just have 1 cent dollar amount. After that first night, you have 2 now. So that would be 2 cents. After the next night, doubled to 4, then doubled to 8, then doubled to 16. So your money is doubling as well. So if we kind of generalize this, remembering my list of powers of 2, this matches that list perfectly. So on the 3rd day we have 8. 2 to the 3rd is 8. On the 4th day we have 16. 2 to the 4th is 16. So it looks like on the day T we have 2 to the T pennies. Which means to get the dollar amount, we would just take that number and times it by the value of a penny, 0.01. So let's answer a quick question about that. How much money will you have after 25 nights? So 2 to the 25th power, 25 nights, 25 doublings, and if we times that by a penny, we'll get our answer. 2 to the 25th. Now go out of the power on the calculator and times it by 0.01. And oh, I'm still in scientific notation, which makes it look like $3, but it's not $3. So if you are like me and you left your calculator in scientific notation, go down to normal again, and then you just hit enter and it'll recalculate. So shockingly, you have $335,544.32. And maybe you weren't expecting it to be that much. I don't know. But I want a magic penny. And if I ever get a magic penny, I will give you all one of the doubled pennies so that you have your own magic penny. All right, last parable. Parable number 3. Suppose you place a single bacteria into a bottle at 11 o'clock a.m. It grows, and at 11:01, it divides into 2 bacteria. And then those 2 bacteria grow, and at 11:02, it divides. So now we have 4 bacteria, and so forth, continuing to double. Now we have 8. So the bottle is full, so they continue to divide, and the bottle is full at noon. So because that was 60 minutes, that means we have 2 to the 60th bacteria. Because it started with at 1 minute, there was 2 to the power 1. And after 2 minutes, there was 2 to the power 2, which is 4 bacteria. So 2 to the 60th bacteria is when it is full. That would be a disaster for the poor bacteria because now their bottle is full and they're going to start dying. But anyway, we've got loads of bacteria at noon. So here is our question. First part, when was the bottle half full? Second part, how many bacteria are in the bottle at 11:45? And then the third part, what fraction of the bottle is full at that time? So first one, when was the bottle half full? Well, it was full at 12, and it's doubling every minute. So it would be half full. It just doubled. It doubled in that last minute. It would be half full 1 minute before 12. So at 11:59 is when it is half full. And then in that minute after, at noon, is when it doubles and is full. And that's kind of weird and crazy to think about, but it's 11:59, half full at 11:59. All right, how many bacteria would be in the bottle at 11:45? Well, 45 minutes have passed, so that's 45 doublings. So that's 2 to the 45th power. It didn't want you to even put that in your calculator. It just wants it in exponential notation. So you would just literally type in 2 to the power 45. All right, last part is the most tricky. What fraction of the bottle is full at that time? So remember, the full bottle has 2 to the 60th bacteria. Well, at 11:45, we just calculated that there's 2 to the 45th bacteria. So the fraction of the bottle that is full well, we have 2 to the 45th, and the bottle fits 2 to the 60th. So this would tell us the fraction of the bottle that is full at that time. Now, pro tip, you can't just type this into your calculator like that. I mean, you could, for sure. But the problem is, if you type it in like this, the calculator gives you a decimal answer. And even if you try to convert it into a fraction, it won't. The calculator is only keeping track of a certain number of decimals, and anyway, it's having some problems. So we have the joy of trying to simplify this on our own because my math lab wants a simplified fraction as its answer. So here is how I would do it. Remembering our exponent rule, now, usually we use this exponent rule to combine two exponentials and we add their powers together, but I'm actually going to use it in reverse, and I'm going to use it to separate that 60 into a 45 plus a 15 so that my expression looks like this. So I still have 2 to the 45th on the top. I'm going to separate it as a 2 to the 45th times a 2 to the 15th. So I just broke that 60th power into two exponentials. Now the reason I do that is because this one cancels out. It's the same on the top and the bottom. So our fraction now looks like this. Now, even if you type that into the calculator still can't handle it. It's the same number after all. So what we're going to do, can't get a fraction from that. What we're going to do is just ask the calculator to help us with that, and then we will type in our answer with the 1 over. So 2 to the power 15 is 32,768. And that is our answer. That's the fraction of the bottle that is full. So it's crazy to me. Even at 11:45, the bottle is still essentially empty. I mean, it has almost no space being taken up. And then it's half full at 11:59 and then full at 12. It's pretty crazy. Exponential growth is pretty crazy. That's it for 8A. I'll get some more videos posted this week as well. Please, please, please let me know what questions you have. If you prefer just getting written question help, I can send you pictures of some written help or written explanations. If you want to meet on Google Meet online, we can work through some problems together. Or if you want to just FaceTime me, I've been FaceTiming Millie to help her with hers, which is so much fun. Please, please, please let me help you if you are stuck on things. This lesson, this homework assignment, I don't know what due date it is set at for in my math lab, but I'm going to change it to Sunday night. So but you'll have 3 of them due on Sunday night. So on April 5th, I will have 8A, 8B, and 8C due. We were actually supposed to do them last week, but it's okay. They're going to be due on April 5th. I'll get my math lab to reflect that. Please let me know if you have questions. Thanks so much.